So today I would like us to continue looking at something called disjunctive normal form. This is what I want us to look at. Disjunctive normal form. So what really happens is when you have the example that we just did, how many variables did we have? How many inputs did we have? 2 inputs, x and y. We have seen other examples where we had x, y, and maybe z, 3 inputs. Okay. Now you notice that when you have Boolean expressions with 2 or 3 variables, it's somehow very easy for you to simplify. It's easy. Whereas the number grows to 4, 5, 6 inputs, it becomes a bit difficult for you to simplify the expression. You might apply the laws of logic, but you will see that it will take you too many steps for you to come out with the result. So what has happened is some techniques have been developed which will permit you to simplify a Boolean expression into And one of these techniques is called the Cannon map. Okay, so I was saying that when you have multiple or more than 2, 3, 4, 5 variables, as the variables increase, you find out that even the laws of Boolean algebra will become very, very difficult for you to simplify an expression. Yeah. So the only way for you to simplify this expression now would be to use some other techniques. And one of these techniques is something called the Cannon map technique. So we're going to use a Cannon map technique in this section of this course to see how to simplify a Boolean expression. Okay? Now, but the first challenge is that for us to use the Cannon map, we need to be able to put the expression in something called the disjunctive normal form. We need to be able to put the Boolean expression in a disjunctive normal form. So if you look at the result that we just had earlier, let me just go back to this example that we were doing. Let's just look at the output. Okay. Now, I'll just use this line and ask if it's... So if I use this line, for instance, xy plus y, this is an expression. This is a Boolean expression. What I can tell you about xy plus y is that it is not in the disjunctive normal form. Xy plus y. And what is the reason? Why is it not in the disjunctive normal form? It is not in the disjunctive normal form because each and every term of this expression doesn't contain all of the variables, or at least a complement of the variable. Are we there? So x plus y is not in disjunctive normal form. Now if I did xy plus x prime y prime, for instance, this expression, so I'm looking at xy plus x prime y prime. You can be writing it so that you can easily see xy plus x prime y prime. Now if you wrote that expression down, you will see that that expression is in disjunctive normal form. And the reason why it is in disjunctive normal form is because each and every variable, or at least a complement of that variable, is found in each of the terms. Do you know what a term is? A term is simply separated. One term is separated from the other term with the plus sign. Are we there? So if I added another term here, for instance, xy plus x prime y prime plus, let's say, x plus xa, then my conclusion is that this expression is not in disjunctive normal form. Why? Because the third term, which has just an x, doesn't contain any variable of y. Are we there? Is it clear? Okay. Now let me write an expression now and ask if it's in disjunctive normal form. xyz plus xy prime plus x prime y prime. And my question is that expression in disjunctive normal form? So I'm going to put terms, the first thing that can be considered the first term. So because the second and the third terms doesn't contain any variable of z. Is that not it? Yes, because the second and the third terms contain no variables of z. So now we are left with a challenge. How can we transform an expression which is not in disjunctive normal form to become an expression in disjunctive normal form? So to do that, we are going to exploit, so we have the disjunctive normal form. So to get a disjunctive normal form, we are going to exploit the following Boolean expressions. The first thing we are going to exploit is that x plus x prime is always equals to what? Something and its complement. X plus its complement is equals to what? Desmond, are you sure with us? You have to answer questions now. Don't be putting it down. X plus x prime is equals to what?
Why?
Is equals to. The student here says x, that x plus x prime is x.
1.
It's 1, good.
1.
X plus x prime is 1. It's 1. Something or its opposite is 1. Always true. No. So we're going to exploit that fact. And notice that whether it is t plus t complement will be 1, anything plus its complement will be 1. Also notice that, let's say z multiplied by 1, or use a dot for multiplication, is equals to what? Anything multiplied by 1 is equals to what? Anything multiplied by 1, z multiplied by 1 is z. Can we agree that it is z or is not z? Some people are just dreaming here. I don't know if they are with us. Z multiplied by 1 is z. I want you to see I want you to see something. Which means what? Which means that z multiplied with what is 1? X plus x prime, for instance, right? Is still equals to z. Is that true? Is it true? Are we there? Is z dot z plus x dot times x prime equals to z? If that is true, then it means that I can always multiply an expression by x plus x prime or y plus y prime and nothing will change. So it means I can equally say this is this plus y prime. To be equals to z. Do you see that? So even if I multiply that expression above again by y plus y prime, I should still get z. If I multiply by w plus w prime, I should still get z. Nothing has changed because I'm simply just multiplying by 1. Is it okay?
Yes.
Yeah, it's okay now. All right. So what happens is the technique is that in disjunctive normal form, whenever you want to introduce a particular variable in a term, if say z is missing in a particular term, I want to introduce z, you simply multiply that term by z plus z prime. Are we there? If in a particular expression, a particular term, let's say y is missing, I want to introduce y to that term, what do? You multiply that term by y plus y prime. Because we know that y plus y prime is 1 and nothing has changed. And we know that z plus z prime is 1, nothing will change. Okay? So we're going to exploit that to transform our Boolean expressions into the disjunctive normal form, which will contain all the variables. So now if you look at the expression that we have on the board now, see that there's a need now to introduce z and z in those two terms, right? So how do you introduce z and z? So I'll just do it on the, so try to introduce z and z. So what I have there is the expression is xyz plus xy prime plus x prime y prime. See that we are trying to introduce z in the last two terms. So how do I introduce z there? I simply multiply by z plus z prime, knowing that z plus z prime is equals to 1. And multiplying something by 1, you don't change anything, because it's still itself. It will still become itself. And now plus x prime plus y prime, and now we multiply by z plus z prime. Once we do that, now we'll now simplify, we'll now expand. So try to expand the expression and see what you get. And we don't have time. Okay, so if we were to do that, it will be x, y, z here, plus x, y prime z, I'm expanding, x, y prime z prime, plus x prime y prime z, plus x prime y prime z prime. Okay? Now it took me less than 10 seconds to do that, and you have been looking at it for the past 5 minutes. That's the expression. So we'll see if some terms are similar, then we can remove them, because we know that x plus x is not 2x, it is x. So if a term repeats and there's addition, you just need to keep one copy of that term. So is there any similar term here? Are there similar terms? X, y prime, z, x, y prime, z prime, x prime, y prime, z. So if you look at it keenly, you see that there's no similar term, right? Which means that that's the answer. Which means that what you have here, x, y, z plus x, y prime plus x prime, y prime, is not in disjunctive number form, but you can transform it to disjunctive number form of this expression.
So that's similar terms.
They're similar term, okay. X, y. Which?
Y prime z.
Tell me that the second and the fifth term are just which terms? The first and the third, the two last, they're not similar now. I missed the prime, that's why. There's a prime there.
The first term and the fourth term.
The last two terms.
They're not similar. I've changed, there's a prime here.
The last two terms are similar.
They're not similar. This one has z prime, this one has just z. Have you seen that? I've just added the prime. Yeah, it's not even similar. This one, no, it's not. Have you seen that it's not similar? I made a mistake initially and I did not put a prime. So just look at it now.
Okay.
1 plus x is true x.
All the terms are different, right? Okay. So we are saying that this equation, let's say this equation, let me start doing some maths here. Maybe one you see maths. Equation 1. So we are saying that equation 1 and equation 2, they are similar. Or they're equivalent. I could say they're equivalent. Okay? So that expression there is equal to this other expression down. But what is the difference between those two expressions? One is in disjunctive number form. Equation 2 is in disjunctive number form. Equation 1 is not in disjunctive number form, but they are equivalent. Are we there? Yes, they're equivalent, and they're equivalent because we just added just one. We're just multiplying those things by 1 and have expanded. Now they're equivalent, but what else can you say? Looking at it, you see that the disjunctive number form looks more complicated. It's more robust. It looks more. It has more terms, right? 1, 2, 3, 4, 5 terms. The other one had just 3 terms. So you see that the equation looks more robust. So, but why do we choose to leave from something that has 3 terms and we're going to something with 5 terms? Is it for nothing? Is it just complicated for nothing? The answer is that it's not complicated. We are doing like that because we want to employ a technique which is called K-maps. So a K-map is just like a kind of a table that you draw, and once you draw that table, you'll be able to put some numbers within the table, and then it's going to help you to simplify the expression. I don't want us to go very, very fast. I want to give another expression and ask the students now to see if they can put that expression in disjunctive number form. So I'm giving you an expression C, which is say yz plus x plus x prime z. So that's the expression. C equals to yz plus x prime z. Write in disjunctive number form. DNF is disjunctive number form. That's how it's abbreviated. Write that expression in disjunctive number form. That there are three variables x, y, and z that are involved in this Boolean expression. The first term doesn't have an x, so you introduce an x to it. So, introduce x there. The next term doesn't have a y or a z, so you introduce y. And you also introduce z. And the last term there doesn't have a y, so you introduce y. And if you have to expand, you have this plus x prime y z plus xy. Okay, I see. Maybe you have to be this one now. There's a big bracket. You have to be very, very careful, even though you miss a term. So I will do the first bracket with x, and then do this z later. So I will do xy plus xy prime, all of that in a bracket, multiplied by z plus z prime. And then that plus here I have now x prime y z plus x prime y prime z. And if I go ahead to simplify, I'll have this plus xy. Now I'm taking the z. I'll take the first z there. Then I also do that and take the next z prime, the same first term here with the second term, z prime. Now I use the second term here with the first, and then here I use the second term with the second term, the xy prime z prime. Then now add the last two terms here, x prime y z plus x prime y z. So let me just expand this so that it comes on one line. Yeah. So if you look, you should have a couple of similar terms. I see there's just one x, y, and z. So x, y, and z. The second term here, x prime. Let me see, is it similar? Yes, so it's similar with this, and also with this. So there are three of them. So you have x, y, z plus. So what we are saying is that I'll just delete when I use a term. I'll delete. So this term is gone. I'm able to strike through. Let's just continue. This term has been used. X, y, z prime, x, y, z prime. We have x, y, z prime here. There's just one x, y, z prime, so that's fine. And then we already use x, y. But then there's x, y prime, z. There's one x, y prime, z. Then there's x, y prime, z prime plus x, y prime, z prime. All right. So I think that's what you get. Yeah. Look at it here again. One, two. It looks like I've missed a term here. Let's look at it again. On my screen here, I'm seeing that there are supposed to be six terms. So I work it out from here. X, y, z plus x prime y z, that's correct, plus xy plus xy prime, correct, z plus z prime, plus x prime y z plus x prime y prime z. Okay, so it's correct up to this point. Then I have this x, y, z, fine. Now this expansion here, x, y, z, fine. The next is x, y, z prime, fine. The next is x, y prime, z, it's good. X, y prime, z prime, that's good. And then you have x prime, y, z, and plus x. Okay, this is why I missed it. This is a prime as well. This last term has a prime. And we simplify now. You have x, y, z. So it's just to add that term plus x prime, y prime, Z. So that's what you get. All right. So can we verify in Douala that the expression is like that? Is that okay? If you cannot get the expression now, does it look like it's doable? Normal form. So you should be able to look at any expression and put it into a disjunctive normal form, because that disjunctive normal form that you see holds some particular information that the regular form will not hold. And before we talk about Carnot marks, we're going to look at some an example which will actually help us to see why the disjunctive normal form is important. So I'll just revert to the notes and show you how the disjunctive normal form is very, very important. Now here we have a table, a truth table for some system. So it's a system that has 3 inputs and has the following outputs. So look at the table under section 3.1. Are you looking at the table? Alright, so we said generally when you have a truth table with 3 inputs, how many rows of records are you supposed to have? Or a different number of rows? If you have 3 inputs. Alright, okay. So you see that this truth table actually shows you all possible input combinations for a particular system. Right? Now, look at the output of that system. The output is 1, 0, 0, 0, and so on and so forth. Those are the outputs on f of x, y, and z. Those are the outputs. Are we there? That's the output. Now, if you look at the output, you see that it is not possible for you to tell us if it is an AND operation that is happening or is an OR operation. Can you actually study and see that it is not doing an AND and it's not doing an OR it's not doing a NOT? It's a bit difficult for you to tell the output. It is an AND gate or this is an OR gate. Are you there? Yeah, and the reason is simple. The reason is just because you can only represent this output using an integrated circuit. It's a combination of maybe an AND gate and an OR gate or a NAND gate and so on. By the way, I did not tell you guys that there were other gates like the AND gate, the NAND gate, did I? So I'm going to write here other gates that are possible. There's not much to study about those gates. So other gates that we have not looked at include things like the NAND gate, and the NAND gate is equivalent to the NOT AND. Okay, so if you NOT an AND gate, you have a NAND gate. I'm going to draw the circuit shortly. You also have the which other gate? The NOR gate, which is equivalent to the NOT what? OR, not OR. That's good. You equally have the exclusive OR gate, XOR. Okay, that's the exclusive OR. It's not equivalent to any other thing. It's exclusive OR, it's exclusive OR. Another gate that comes to mind, you can even have the NOT XOR. It's possible. Not, so I can still put a NOT XOR. Exclusive NOT XOR. So this is NOT XOR gate. So these are other gates that you could possibly have, and you see that these other gates more or less is like a combination of the gate and an inverter. So if I were to draw on the board, let me just try to draw for those in this one out of here. Let me just draw the gates. Alright, so a good thing for us is that we have those symbols there already. So there is the NAND, let's see the NAND. Okay, this NAND gate. So the NAND is already there, the small O is on the head, and then you have those 2 pins there going down, so it's just easy. And what we are saying is that the NAND is equivalent to the NOT OR. So I don't know if I really need to draw it here. Maybe let me just use a clipboard and draw it. Alright, so we are saying that for the NaN, something like this is not, and then you have the inverter there. Small head there. So my diagram is very rough. I'm using my mouse to draw. So that is a NaN. That's the NaN. You have the AND and then an inverter, and the symbol for this will just be something that resembles the AND gate, where you have a small O on the head here. This is the symbol of the NaN. Can we see?
Yes, sir.
Yes, it's not. I mean, my diagram is not very good, but I think you can understand. And that's the same for the NOR gate. The NOR is just the OR gate with the NOT at the head, so it's just similar. What is different is the XOR gate, which has the symbol is a bit different. So it's like you see something like this, and then you see the OR gate with that line. I'm sure we should have seen that symbol somewhere before. This joins there, so I'm just drawing it. It's very rough. The diagram is very rough. It doesn't give a good picture, but I think you can always. So it's something like that. Exclusive OR. And what I was just mentioning here is that the exclusive OR, which we always represent with something like X plus. I don't know if you remember how we represented the exclusive OR. It was X, then the plus was circled, plus Y, and we said it was equals to either you get X and you don't take Y, so that's an Y prime, or you don't take Y and you don't take X and you get Y. So if this is the exclusive OR, then that's what you get. Yeah, there should be a circle there. Where's the annotation 2? Where's my mouse? So there should be a kind of circle there. Okay. So exclusive OR is something like that. The O is there. X plus, which is circle, plus Y should give us that. That's the exclusive OR. So, and you can see that you can actually draw using the basic components. You can actually produce the XOR gate. So at home, you might probably want to try to see if you can use the AND and OR gate to produce, and the inverter to produce a XOR gate. All right. So that was just an aside, just to record that there are other kinds of gates. Is that okay? All right. Let's just continue. Okay, so we just established that if you have 3 different inputs, you should have 8 rows of record, and there we have all the 8 rows, and those are the output. Now X here could stand for, let's just say, the traffic light at CIB junction is green. Y could stand for the traffic light at checkpoint junction is green or is red, for instance, and Z could stand for, I don't know, maybe the street light is on. Okay, it could just be those things. And we are saying that f of x is actually giving us the acceptable conditions that we want to see in that system. So if f of x, y, z is 1, it means that we want that kind of system to exist. It means that we want that when x is 0, y should be 0, and z should be 0. I'm looking at the truth table. And we're also saying that if you go now to the fourth one, that's the fourth row, we're also saying that when x is 0, y should be 1, and z should be what? Z should be 1. And we're also saying that when x is 1, z should be 0, and y should be 1. Those are the positive outcomes that we want. Okay? Those are the allowed outcomes that we want. So it means that we are going to produce the output or the Boolean expression for this circuit using what we call the sum of the mean terms. The sum of the mean terms. And what are the mean terms? The mean terms are simply those terms where the output is 1. The mean term is constructed from the inputs where the output is 1. So it means that if you look at it already, you see that how many mean terms are we going to have? 3 mean terms, because that's the only time when the output is 1. So it means that f of x will just be the sum of the mean terms. And how do you get a mean term? It's very, very simple. So if you look at the first one, the mean term that you get from the first one is x prime, y prime, z prime multiplied. X prime, y prime, z prime. Because the bottom line is that you want to have 1 as the output, which means you need to prime the x so that you have a 1. Multiplied by y prime and also multiplied by z prime. Now the contribution from the second mean term, which is actually the fourth row, is actually x prime y z. Can you see how to get the second term? The second term there is x prime y z. And the last mean term, which happens to be the C term, 1, 2, 3, 4, 5, the C term would be x y prime z. Are we seeing the pattern, how you do to achieve those stuffs? Yes, so that's the pattern. So it means that if I give you a table like this and ask you for the Boolean expression, then you just need to use the sum of the mean terms to get the answer. Yes. So it means all of this table, the information in this table can be simplified to f of x, y, z being equals to the expression that we have here. So the first question I have for you is that expression in disjunctive normal form? The answer is yes.
Yes, sir.
Yes, it's in disjunctive normal form because all the variables are found in each of the terms. So which means that when you have a real circuit, this is the starting point. You start by representing your circuit like this to say that if this is this operation is allowed, this should be true, this should be false, this should be true. And once you have that truth table, you can now transform that truth table into a Boolean expression. Now I want you to apply what we have just done now to the truth table for an exclusive OR. Can we construct the truth table for an exclusive OR? So I'll just look at an exclusive OR, put the truth table. Sorry. So I want to put a truth table for an exclusive OR. So exclusive OR, you have x, you have y, and then you have x or. I'll just use the plus sign here for the x or y, but it's exclusive. So maybe I should have used something else, not the plus. Let me use something else, not the plus. Let me use, I don't know what I can use that will resemble the plus. I'll use the hash. Yeah, so I'm using that for exclusive OR. So if we follow the order, we start with 0, 0, and 0. 0 or 0, exclusive is 0. The next is 0, 1. 0 or 1 exclusive. 0, 1. Output. Output exclusive or x 0 or 1? 1, okay. Yeah, now 1 or 0? 1, okay. Now 1 or 1? 0, okay. Exclusive OR. So, and if that is the truth table for the exclusive OR, what I want you to notice is that the second and the third line, which have 1 as the output, will contribute to producing the output for this table, which means that the mean term will come from the second and the third row. Okay, and if we were to look at that, you will now see that the output is actually x prime times y, which is coming from this second term, x prime times y, and the next output, which is from this one, is plus x times y prime. Okay, so we're actually saying that exclusive OR x or y is actually equivalent to x prime y plus x y prime. And you should know that this expression is in disjunctive normal form. It's in disjunctive normal form. So it means that if you went back to all the truth tables that we have been doing before, you can actually write that expression in disjunctive number form, the output, by looking at the mean terms. And the mean terms are those terms where are generated from those terms where the output is a 1. Is that okay? Good. So you start seeing that the mean terms are very important, the disjunctive number form is very important. So once you have the expression, if there are just 2 variables, you see that it's very easy for you to simplify. If there are 3 variables, it may be easy for you to simplify. Now, but once the number of variables will increase from 3, 4, 5, it will be very, very difficult for you to simplify this expression. So we are going to now employ a technique called the K-map to help us to simplify Boolean expressions of more than maybe 3, 4 variables. Are we there? Alright, so I'm going to show you a particular expression in disjunctive number form. Okay, I'm going to write an expression in disjunctive number form, and then you are going to produce the table which corresponds to that expression, because that's one other thing that you can be asked. Alright, so I'm going to give you an expression. Consider the expression, let's say d to be equal to xy z prime plus xy z plus x prime y z plus x prime y prime z prime. So please take down the expression. The expression is d equals to x y z prime plus x y z plus x prime y z plus x prime y prime z prime. Yeah. Imagine that we told you that this is the output for a particular Boolean, for a particular digital circuit. Can you draw the truth table? Can you draw a truth table for this Boolean expression? Draw the truth table for this Boolean expression. Draw the truth table for this Boolean expression. So that's the question I'm asking you. Draw a truth table for this Boolean expression. Is the Boolean expression in disjunctive number form? Yes, okay. So draw the truth table. I'm not saying you should simplify it, so you're instead drawing the truth table. So draw the truth table. That's good. Alright, so that's what you get. So basically you have a truth table with 3 inputs, which means you have up to 8 rows of record, and then you're going to identify, you see the contribution. Generally the output should all be 0, but now you look at the terms that will contribute to that table, that z function. Then you see that when you have x being 1, y being 1, and z being 0, the output should be 1. That's the contribution of the first term there. And then you see that when you have x, y, and z all being 1, then the output should be 1. And when you have x being 0, y being 1, and x being 1, the output should be 1. And where you have x being 0, y being 0, and z being 0, the output should be 1. Alright? So that's what you do. And if you do that, you get the output. So let's see how to use Canon map. Is there anybody who could not generate a truth table? Those in Douala, is there anybody who's having difficulties? Now the secret is that you must. Sorry? Is there anybody who could not generate a truth table? Anybody? But is it okay?
Yes, sir.
Alright, so we are continuing.
Yes, sir.
Yeah, okay. So the bottom line is that you see that we're just playing around the disjunctive number form, and to show you that from the truth table you can come out with an expression in the disjunctive number form for any complex circuit. Because remember, if you're to design a digital circuit, you are going to start from a truth table. You look for some variables and let them represent certain components in your circuit. A component could be, X could stand for the security light is on in the corridor. The security light is on. B could be the television is on. C could be the room in the light is on. In your room is on. And you can come out with a digital circuit in such a way that if the security light is on, then maybe the light in your room should be off. I don't know if you understand. Or if the light in your room is on and the TV is on, then the security light must be on. So it means you first of all come out with the possibilities, how you want the system to behave, and then once you have those positive inputs, you are going to use that to come out with a Boolean expression. And once you have that Boolean expression, you can now simplify the Boolean expression to now come out with a more simplified expression, which you can implement. Because there's no point implementing a Boolean circuit with 100 components when you could use 10 components to do the same job. So that's why you will simplify. But now we are telling you that when you have many inputs in your digital circuit, it becomes very, very difficult for you to apply the laws of Boolean algebra to simplify. It will take you more time to simplify. So what you need to do is, if that expression can be in disjunctive number form, then you can employ a technique on it, which is called Carnot map. Are we there? To simplify the expression. Is that okay? Is it okay here? So everything we are doing this far is to help us to use Carnot maps. We are trying to justify why you have to learn Carnot maps. That's what I've been doing since morning. So it means that Carnot map is important now. So everything we have been doing since morning is to justify why we have to use Carnot maps. Alright, so I'm going to now move on to Carnot maps. Unfortunately, you may not have the notes, but the note is in the textbook that I gave. The extra the note, you may not have it, so I'll try to be writing mostly on the board. For those who are online, you can follow from my screen. I'll just try to project a section of Carnot maps. How the notes there has disappeared. So let me just see. Okay. All right. So can we see my screen from Dwala?
Yes, sir.
All right, good. So I want us to look at the Carnot map section. I just want to go down Carnot maps. Okay. So Carnot map is simply like a kind of tabular form of representing information so that you can easily group the terms. So what happens is when the expression is in disjunctive number form, you'll be able to form some kind of a table. Now look at the first. You have the. You don't have that, but I'm saying it's in that textbook. Do you have the textbook on the screen? But you have the textbook online now. But don't really bother much. You can read that at home. I'm going to be writing on the board. So now I want you to look at this table that we have here. So see that when you have two variables, x and y, then you can produce a Carnot map of the form as you have there. I'll just try. Or in fours or in eights. Okay? That's how the grouping happens. And they must be adjacent. So there are some rules in grouping. I just wanted to look at the section on the rules that you have to follow when grouping the terms. So those who are joining us now from Douala, I know the thing break off. Can you actually see that the expression xy plus x prime y plus x prime y prime can lead to this kind of setup like this? So you see now that this first one up here is actually xy. The next one below is x prime y, and the next one here is actually x prime y prime. So that's a truth table when you have just two variables x and y. And the bottom line is, how do you simplify the Boolean expression now? What we need to do is we need to group terms. So we need to follow some rules, and the rules are simple. We group in even numbers. So we group twos, 2 ones, or we group 4s, 4 ones, or we group 8 ones. Okay? And we can only group adjacent terms. We cannot group like in a diagonal fashion. So you cannot group like this. You cannot choose to say that I can group this term and this term and this term. Okay? So it must be horizontal or vertical. So that's how the grouping will happen. One other thing is that when you have a bigger map, you can actually group a term here with this other side and this. We'll see that later. Because this map is like it's actually considered as this. It means you can take something on this side and group the back, this other side. But it doesn't really apply in this case because this case is just four cells. So there's no point in you grouping something backwards when you can just group it in front like this. But in the case where you have a bigger cell, where you have 1, 2, 3, 4, let's say there are 2 zeros here, you can actually group this term with each other backwards. This one can go backwards. So it's a bit complicated, and the reason why you say I can go backwards is because the way we always draw this thing, this term and this other term always have a similar term. When you see or go to a higher dimension, you see that the edges are always related. But for now, it's not related because it's just a two variable Cannon map. So now, how do we go ahead to simplify? Well, I've said I can only group in twos. So this table below here shows you how you're going to do the grouping. And if that's the grouping, see that this term, this first vertical term, will give you y as the output. Because y is actually common. And the other term, which is horizontal, will give you x prime as the output. Because x prime is common. So what I'm saying here is that when you group terms like this, and you want to get the output, so you group like this, like this. So if this is A and this is B, this first grouping, because y is common for this grouping, the output will be, the simplification from this column will be what? Will be y. The contribution of this column to the answer will be y. And look at the next column. What is common here? X prime. The contribution of that will be X prime. So we are saying that the expression that we had earlier is equivalent to y plus X prime. We have the expression that has 3 terms. Xy plus, what was it again? We had xy plus x prime y plus x prime y prime is equivalent to y plus x prime. So the Cannon map, we are not simplifying things, we just look at it from observation and write the answer. The only thing we need to do is how do we group our terms. If you cannot group the terms, then there's no way for you to actually tell the answer. So the real big challenge with Cannon maps is how to group the terms. So once you have the expression in the disjunctive number form, you draw your Cannon map, this is a K map, tabulate it, and then you now put the ones where they're supposed to be, and then you go ahead and do the grouping and come out the simplification. With 2 dimensions, it's a bit easy. It's too easy, and you may not think that Cannon map is a very powerful technique. Okay, so let's increase. Let's go to a higher dimension. Let's go to a higher dimension. Now we have 3 variables. Higher dimension. 3 variables. X, Y, and Z. So once we have 3 variables, we'll still put x and x prime on this side. But here you have y and z, y prime, z prime, or y, let's see, y prime z. And then you have now y prime, z prime, and then which one I have now? Y, z prime. The order is very, very important. If you change the order, many things will go wrong in your life. I'll tell you what to guide you when you are constructing those terms up there. Something has to guide you. Something guides you when you are constructing these things. What you observe is that between every 2 adjacent terms, there's always a common variable there. Between every 2 adjacent terms, there's always a common variable. Which means, so what I'm saying is that between every 2 adjacent terms, when you have 3 variables, this is how you're going to arrange it. Between every 2 adjacent terms, there's always a common variable. Notice that between yz and y prime z, what's the common variable there? Z. Between this and this, Z is common. Between this and this, what is common? Y prime. Between this and this, what is common? Z prime. Are you seeing it? If you're to do it freestyle, what are you going to do initially? You come here and say, okay, there's this, there's Z, Y prime, there's Y prime, Z, there's one, then there's one again, Y prime, Z prime. You do this, let's see what is the common thing. There's Y here. Y is common here. Between this and this, what is common? Nothing is common here, so there's trouble. So that's what will guide you when you are constructing your Canoma parameters. If you just choose those things at random, they will not be common. Which means when you group a term like this, you don't know how to simplify it because there's no the adjacent rows or columns are not common. So that's what is going to help you to simplify. Are we there? So that order is standard and is important. You don't choose the order. You don't get up one day and start changing the order. So those are the things that you have to learn. Alright, this example here produces a Canoma map of this form. You don't need to start the disjunctive normal form and then start plotting those things. You should be able to, by this time, come out with that 1 1. Everyone plays a 0 now. But we don't care. 0 is now, we don't care. There's a case where you have 0 and there's a case where you have don't care condition, which means whether it is 0 or it is 1, you don't care. So you see in another truth table where you came up with something like X here or Z, I think they use Z. They put a Z here. The Z here means that they don't care what is here. It means that whether it is a 1 or it is a 0, they don't care. But who is going to care? When the person to care is you, because when you are grouping the terms, you are going to use this don't care condition to favor you. Which means that if I were to group, I'll choose to group like this, 4 of them. Even though this don't care can be a 0 or a 1, I'll prefer to claim that it's a 1 now because it's going to help me to simplify this expression. Are you getting the don't care condition? Yes. But if I put 0 here, 0 here, it is 0, it is not don't care. You cannot change the 0 to a 1. But you can change the don't care to a 1 to help you to simplify. Or if you see that they don't care, let's say you have something like this, you see that this don't care will intermediate to be complicated. You assume that it is a 0. Are we seeing what don't care is all about? But when we are teaching, the first thing is that we don't teach you about don't care. So take out don't care from now. We care. Okay, so alright, so I was just trying to talk to the class here about another condition which is usually called a don't care condition. And with a don't care condition, what happens is you may be given a Canoma map and they may say that it doesn't really matter whether, for instance, you have a 1 in this field here, let's say below somewhere here, you have a 1 or you have a 0. It doesn't really matter. If a 1 there or a 0 doesn't really matter, then it means that space actually has something called a don't care condition, which can be represented with a D, let's say the letter D. Now, when you have a don't care condition, you always use it to your advantage when you are decomposing or when you are simplifying your expression. Because in the case where the don't care condition will help you to simplify, then you assume that Z there is a 1. So if you know that if you change the D to a 1, it's going to help you simplify, then you presume that the D is a 1. And when you see that the D there will make the thing to be complicated, or a 1 there will make it to be complicated, you assume that it is a 0. Because it doesn't change anything, it doesn't change the logic of the circuit, but it's going to help you to simplify the expression more, which means at the end of the day, you are going to use a smaller number of components to construct your digital circuit. Are we good? Good. Alright, so let's see how to group when you have something like this. So we said you have to group in blocks of 4, blocks of 8, or groups of 2, or I don't know if you can have 16. If you have a very big Canoma, you can have up to 16. Okay? So if you add another variable here, 1, 2, 3, 4, then you see that it's 16. Are we seeing it? If you have 4 variables, it's 16. You say I'm joking. You have the more variables you have, you just make these things bigger. But it is even easy with a Canoma. If you were on a truth table or with the other expression, it could be as long as from there to here. But when you put that information in the Canoma, it comes in one compact box where you can just group and simplify. That's why the Kano map technique is important, because it helps you to easily simplify an expression. So in this particular case, how am I going to group? We can group 4. So I just see that I'll just put this 4 in the group. Okay? And if I put this 4 in the group, how do I treat this one? Do I treat it alone? If you treat it alone, then you are losing. So you prefer to treat it with this other one. We cannot group 3s, because what happens is that there's no relationship between from here right to this point. There's always a relationship between adjacent. So you only group this and this, you find a common column. If you group up to this point, you will not find a common, this one is common. You have to group 2s, or you group 4s, or you group 8s. And you can group a term here with a term on this other side, so long as a 1. But in this case, it's not a 1, I'm not grouping backwards. Let's see it. So if I had a 1 here, I could choose to group the 1 here, or I could choose to group the 1 backwards. So you might have options. So but the bottom line is that you have to group every term, and each term that you cannot group, then you are going to write it out explicitly. Imagine that there was a term here that we could not group, because there was no 1 here. It means at the end of the day, this term here will be what? X prime, Y, Z prime. There is a load, you cannot group it to another term. I'm just looking at a case where the 1 is isolated, where you cannot group it to another adjacent term. Alright, so with this, the first grouping will fall. What does it give as the output? See that, what is common? When you have a big block, look at what is common. What is common here? I see that Y prime is common. So it means that this 4 will give me Y prime. That's all. That's the only thing that is common. The every thing is changing. So you see everything is changing, it will cancel out. Come out to this other one. I see that what is changing? Or what is common? Z prime is common, right? What else is common? X is common. So the answer is X, Z prime. Looking at it, Desmond especially. So look at it very well. Don't look at me. No, do not fabricate that thing. Alright, so guys, look at how the grouping has been done. Is it clear there? So you have to group in 4s, or you group in 2s. So the first grouping of 4, what happens is, if you look at it keenly, you will see that in that grouping, Y prime is common. Y prime is common. Do I have something else there? What do I have there? Y prime. Okay, it's Y prime here. So you see that Y prime is common. Therefore, that grouping of 4 will give you Y prime as the output. So it simplifies to Y prime. Now the next grouping of 2. See that X is common, and also Z prime is common. So if you use the further X is common for the grouping of 2, and Z prime is common, then you get another term which is X, Z prime. Is that okay?
It's okay, sir.
Yeah, it's okay. All right, that's good. I hope you are speaking for. I hope the class is also saying it's okay. Please, whatever you hear is okay. Don't sit quiet. If it's not okay, you tell us it's not okay. Because we have people there who just sit and just follow the chorus.
It's okay for the class.
All right, that's good. Okay, maybe we should always have a class delegate when we are doing a class session so that he can speak on behalf. So sometimes some people have their mics mute and they cannot easily react. So one person should always have their mics on so that you can always react on behalf of others. All right, so if you look at it there, we have the rules of this game indicated clearly. All 16 ones. So if you have all 16 ones, let's see, that should be in, when you have 4 variables, then the output should be all 16 ones. Let me see. Okay, if you have 4 variables, then you have up to 16 ones. And if you have all 16 ones, the output is just a 1. 8 ones, that's how you can group. You can group all 16 ones. You could group 8 ones. 4 by 2 or 2 by 4. So you can do 2 by 4 or you can do 4 by 2 grouping. Then how else can you group? This includes broken rectangles, such as rectangles consisting of the first and the fourth row. So that means that you can group backwards. You can take a first row and group with the last row, meaning that you actually group something out of the Cannon map. The examples there will actually show you how that is done. So you don't really need to bother much about what I'm saying. Those examples there would help you. So what you notice is that all what I'm saying there is in the textbook. The textbook I put online. All right, bye. Okay, good.